Hello everybody and welcome back. Last time we started talking about waves and what a wave is. Now today we're going to continue our discussion and figure out what waves can do. So let's think about how waves differ from an actual particle or an object. Back before when we were talking about collisions and momentum, we might have had two objects, whatever they were. Here's two balls, and they are going to be moving in a head-on collision. Eventually they'll move into each other and they will crash. Bang. They exert forces on each other, which causes them to eventually recoil and go back in the other direction. At least that's one possibility. So the idea is that objects will actually exert forces on each other, which will change their motion depending on how exactly they collide. Waves have the sort of liberty to pass through one another. And when they do, something weird happens that real objects cannot do. And this is what we know as wave interference. So imagine we have two waves. Here's one wave. And here's our second wave that looks exactly like the one we started with. So our goal is to have these two waves pass into each other. They might be coming, here I've drawn them side by side, but they might be coming head on like they were with these two spheres here. Our goal is to figure out what happens when these waves pass through each other, and the trick is basically simple addition. When these waves interfere with each other, they're going to sort of add together at each point, point by point along the entire structure of the wave. And when they do so, we note that, whenever this wave is up, this one is also up. Whenever this wave is down, this one is also down. So when these two waves add together, we essentially get a much taller wave. And they're going to add together based off their amplitudes. So if this wave had an amplitude of 5 and this one had an amplitude of only 3, our final wave, once they add together, is going to have an amplitude of, you guessed it, 8. So that's it. Waves that are together, we call this in phase. They add together at every point, giving you a wave essentially twice as tall. So in this sort of mode of interference, we call this constructive interference because the waves are building each other up. They're constructing a larger wave. And if we change the amplitudes of this wave, the result would be just the sum of the two amplitudes. So our amplitude is sum of the amplitudes. If I change that to 12 and 12, we'd have a wave of 24, for example. All right, that's one way waves can interfere. The other way is, say I'm going to draw the same wave I had before, something like that. And now I'm going to draw the opposite wave. So this one starts going down, goes up, down, up, and so on. And so now we know that whenever our first wave is up, this other wave is down. And whenever our first wave is down, the other one is up. So we're still going to add point by point along the length of the wave, but because they're oppositely aligned, one is positive, the other is negative, and if these amplitudes are the same, we get complete cancellation. If they weren't the same, you'd have imperfect cancellation. Say this one, we have 5 and 3 again, we'd have a wave with amplitude 2. So in this case, destructive interference, where they are out of phase, they're out of sync with each other, a little word there, out of phase, we get destructive interference. Where essentially waves subtract from each other. So in this example here, if they have the same exact amplitudes, 5 and 5 for example, they're going to cancel out completely and we get nothing. Flat line here. And this is exactly the principle, roughly, by which noise-canceling headphones work. If you want some peace and quiet, you put on your nose-canceling headphones. That's a very different invention. You put on your noise-canceling headphones, And what they do is they pick up on the ambient noise in the room. So all the little background noises that are happening, your headphones pick up on this. The little chip in your headphones then decides to spit out the exact opposite of those sounds, and you get nice silence. So destructive interference has some actual applications, and so does constructive, but that's just something that's pretty cool, I think. So wave interference. These are two extreme examples. If they were not perfectly in or out of phase, you would get a combination, but all you're doing is you're adding at each point along those waves. So if they weren't perfectly together or perfectly out of sync, you might have to do a little bit more work, but the idea is you're just adding the value of the wave at each point. So in practice, and the AP exam loves these kind of problems, you might have wave pulses coming in at each other. So here's a little axis. Here's a point P that we want to examine the history of as two waves come in. So I might have a wave pulse that looks like this. And I might have a wave pulse that looks like, let's do the opposite. So 1, 2, 3 units long, 1, 2, 3 units long in both cases. We'll say that they're each 2 units away from point P, and they're moving at 1 unit per second. So each of these wave pulses is going to come in, and when they cross point P, we're essentially going to add up the amplitudes of these pulses at each point. So the way I do that is now I'm going to draw a history graph at point P. And I'm going to essentially, draw axes here. So y is my amplitude. We'll say this is 1, 2 amplitudes high, and the same thing over here just to keep things simple. And at 0 seconds, neither wave has moved yet, so the amplitude is still 0. At 1 second later, both waves have crept forward by 1 unit, but they still have not crossed P yet. So at 1 second, our amplitude is still a flat line. And even at 2 seconds, we get nothing. It's not until 2 seconds that the waves start to jump up. And so what we see is the wave on the left here has an amplitude of 1. The wave over here is an amplitude of -1. And so when they cancel, it's still a flat line for that first second. So up until the next second, the third second, 1, 2, 3 seconds away, this one jumps up to 2 at 1, 2, 3 seconds away. This one is at -1. So now we're going to jump up to an amplitude of 1 for that next second. At 4 seconds, I look 4 to the left, 1, 2, 3, 4. It's still at 2 up on the left. We have 1, 2, 3, 4 to the right. That one jumps up to 2, -2 on the right, and so now it flatlines back down to 0. And then finally at 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, both waves have passed that point there, and we're going to jump back down to 0 again. And it will be 0 from there on out because the waves have passed. So what we did here was essentially for each time increment, we looked at, how far away that wave was from the point of interest, and we sort of just added the amplitudes at each point. So we, look left, that number of units. We look right, that number of units. And then add amplitudes at those locations. So we have these two pretty complicated waveforms, these sort of steps that go up and down, and when they cross over each other, all we get is this sort of weird one up step for that duration. So at that point was where they were actually able to constructively interfere, but at every other point they destructed to complete oblivion. So that's just one example you'll see here. All we do is we figure out, how far away that point is. At that point in time, we add up, the respective amplitudes of each form. So that's wave interference. What really makes wave interference interesting is this idea of standing waves. So a standing wave is essentially we have a series of wave pulses coming in, and they interfere with their own reflections. And they do so in just the right way so that the wave doesn't look like it's moving to the left or the right. It just kind of looks like it's standing still, hence a standing wave. And so what we get is that the wave looks like it's standing still. I imagine in this situation, at least one of you has started to try to teach themselves the guitar. And so if we have a guitar string, for example, go ahead, pluck it if you have one. See, you can demonstrate to yourself. What happens when you pluck the string is these vibrations start to happen. They'll reflect off these other boundaries, and as those initial vibrations interfere with their reflections, what you get is not, a waveform like these guys up here that bob up and down and move from left to right, but what you get is kind of, the string bobs up and down. Here's, you can sort of see it smear out among this shape, but what the string does is it bobs up between this maximum point and this minimum point from some resting equilibrium, and this is what we call a standing wave. This particular standing wave would be known as the fundamental frequency. And this is sort of the simplest possible standing wave. The point at the center here, where the wave is at maximum amplitude, we call that an antinode. So this is a region of the standing wave where we have maximum amplitude. The wave moves the most. These points here at the end where the string is fixed down, these are called nodes. And these are regions where the wave does not move at all. There is no node, no motion at these points. So a standing wave is a wave that alternates between regions of no motion, nodes, and antinodes, regions of maximum motion. And sort of what happens is the wave just bobs up and down between these two values here, and the nodes stay completely fixed. So, I said that the fundamental frequency was the simplest possible standing wave. You can get higher versions. And what happens is, for a wave on a string at least, is the rule is that the ends of the string have to stay nodes. So we can have any sort of wave structure inside of here as long as the ends are the nodes. So our first case was our fundamental. So we have node, node, and then an antinode at the center. Now what happens is, in order to get to my next possible standing wave frequency, In order to get nodes at the end, there has to be essentially a node directly at the center. So, I have a node there, and I complete one full wave cycle. And just to sort of illustrate here, what the standing wave does is now I have these two antinodes, and essentially what's happened is these are going to bob up and down. So this one's going to be up, down, up, down, up, down. They're going to go like that. So this we call n equals 1. This is n equals 2 as my next possible standing wave. And we can keep going as long as we make sure the ends stay nodes. So our next standing wave is going to look a little like this. And now I have two nodes in the center of the wave with 3 antinodes. So the n value here represents the number of antinodes. N equal number of antinodes. And we can go to n equals 4, 5, 6, whatever. But let's keep it simple for here. I can't draw all day. So we have n, 1, 2, 3. We want to ask ourselves, how many wavelengths do we have in this fundamental frequency? And we're not counting the ups and the downs. This is just an illustration of the sort of the range that the wave vibrates through. So here we have, we go up and we go back down. We've only completed half a wavelength. We could imagine that there is, an imaginary, complete wavelength outside of the length of the string, but physically all we have is a half wavelength in between here. For our second harmonic, we have, up and then down again, we have the full wave cycle. And then here we have 1.5 waves. So the ends here, it corresponds to the number of antinodes, yes, but more distinctly, it is the number of half wavelengths I have in between the boundaries here. So n is also the number of half wavelengths. And this sort of characterizes the allowed frequencies that can be made by a string system. If my string has a length L, then L essentially has to be some multiple of half wavelengths. Or I guess N. So the length of our string has to be some multiple of half wavelengths. In our n equals 1 case, it's exactly a half wavelength of that frequency. In the n equals 2 case, n equals 2, and L is exactly the wavelength of the system. Here we have 1.5 half wavelengths, which is exactly 3/2 wavelengths. We want to find the special frequencies that correspond to these this system. We can substitute the formula we learned last time, V equals F times lambda, and we solve for lambda as V over F. So now I can substitute in L, let's say 2L is equal to NV over F, or that the special frequencies we get are NV over 2L, where N is any integer value. So now, for a given length of string and for a speed of a wave across that string, we can figure out what frequencies can be made on that string. So this V here, this is the speed that the wave moves across the string. It is proportional to the square root of the tension in the string, and this value mu, it's not friction, it is the mass density. So in other words, it is the mass per unit length of that string. This is the tension in that string. So now think of it. If you ever played a guitar or a violin or a cello, I'm a viola man myself, you tune that instrument by turning a peg at the top and adjusting the tension in that string. So as I tighten the string, I make it tighter, I'm letting the wave move faster along that string, and as the speed gets faster, I increase the pitch or frequency of that sound. So yeah, frequency is analogous to the pitch of the note that is played by that string. Likewise, the big fat strings at the one end of the guitar or the cello, they play lower notes, and as I increase the mass density, the wave across that string gets smaller and it plays a lower pitched note. So everything you'd ever want to know about how sort of a violin or guitar string works is encoded in this simple little equation here. If I want to get higher notes, and it's actually really hard to do on a string instrument, I can excite higher end values for the frequency. If you want to do it on a violin or a viola at least, you can put your finger really lightly on the string and then give it a bow. That'll excite the second harmonic, but it's not really a practical thing to do very often. So it's all here there. Like tuning your instrument, changing the tension in the string changes the pitch. Larger strings make a lower sound. Longer strings will make a lower sound. So for example, a cello plays lower notes than a violin. It's all here. We can do a similar analysis for wind instruments. Basically a flute, where instead of a string we have a tube, and it's open at both ends. We're going to excite sound. So instead of a string vibrating like we did up here, we're going to blow air into this, and we want that air to resonate inside the tube. We're going to get that when the ends of this tube are both antinodes. So it's kind of the opposite of the situation we did before. Here I have air vibrating at its maximum value. At the other end, it's also vibrating at its maximum value. And at the center, because of that structure, we get a node. Pardon my artistry here. So now we have a node at the center, and we have antinodes at either end. So this would be our fundamental frequency. N is now the number of nodes. But it's also the number of half wavelengths we have in our thing again. This is our half wavelength. We go from a peak of the wave down to a trough of the wave, and we still need to get back to the next peak. So the structure is going to be the same. I'll draw n equals 2 and 3 for you so you can see what that looks like. We need antinodes. Now we're going to have 2 nodes, and we have the full... These are much harder to draw. So here's a node there, there's a node there, and now I have an antinode straight at this. You can't even see what I'm drawing. I apologize. And n equals 3. We up the ante here. And now we have to have 3 nodes. 1, 2, 3. So at these points, the air is vibrating the most. At the nodes, there's no movement of that air. And these special frequencies give you the overall structure of what this wind instrument is doing. Because the ends match and we have a half wavelength sort of base unit for this instrument, our formula and derivation is going to follow exactly the same sort of pattern here. So I'm going to spoil it for you because it's the exact same thing. But here, v is not the speed of the wave along the string, it is the speed of sound in air. So that's actually the rate that the sound waves are moving inside the pipe. L is still the length from one end of the pipe to the other, and N is sort of the number of node that we are, the mode or harmonic that we are currently looking at. This is how wind instruments like the flute work, or even like an organ pipe. Brass instruments and reed instruments like a clarinet or an oboe, they work a little bit differently. Unfortunately, I'm sort of running especially long on this video here, so I'm going to cut it short and leave that as a little spoiler for next time, where we'll talk about how a trumpet works. So thanks for bearing with me in these dire situations. Hope you enjoyed this video, and see you next time.